So you can see the structure. Copper attached to 4 ammonia. It is on page number. It is on page number 34 of unit 10. Unit 10 and the unit 10 and the sub unit is 11.2. 11.2. There you see the copper attached to 4 ammonia, and the complex is a square planar complex. You can see the structure of tetraamine copper 2 sulfate or tetraamine copper 2 ion. Similarly, when iron combines with carbon monoxide, it is called carbonyl ligand also. Carbon monoxide ligand, when forms coordinate bond with iron, it is called carbonyl, and the complex is called metal carbonyl. The complex is called metal carbonyl. So iron combines with 5 moles of carbon monoxide, forms pentacarbonyl iron, and this is a metal carbonyl. This is a metal carbonyl. Then this is a metal carbonyl. Then you see then ligands already I have discussed. Unidentate, bidentate, tridentate, and the number of donor sites in a ligand is called its denticity. And EDTA is hexadentate ligand. It has 6 donor sites. You can see the structure also. It has 6 donor sites. Then I have explained you what is ambidentate ligand last class. In detail, I am telling you now. For example, take an example of NO2. NO2 is called nitro group. Here you see nitrogen atom can donate a pair of electron to metal. So if it is through nitrogen, then we can say it is nitro or nitro. It is called nitro. But sometimes NO2 formula is NO2, but the structure is different. It is ONO. ONO, and here oxygen is attached to metal. When oxygen attached to metal, it is called as metal nitride, called metal nitride. So nitromethane, so nitro, one is nitride. In nitrogen atom is attached to metal, and in nitride, oxygen attached to metal. So depending on the attachment of nitrogen or oxygen, the name has been given. For example, one is called nitro, other one is called nitride. One is called nitro, other one is called nitride. So naming is also similar. In the when you have to write the IUPAC name of coordination compound, there this is very important. Some you find in some cases NO2 is there. You find in some cases ONO is there. Then you see that ONO is your nitride and NO2 is your nitro. Then a chelate. I've already told you, chelate means a polydentate ligand simultaneously forms more than one bond with the same metal atom. It forms a ring type structure called a chelate. Question will come, what is a chelate? Then remember, you write that when a ligand is polydentate and it is coordinating with a central metal atom through coordinate bond, then it forms ring-like structure called a chelate. The complexing agent is called a chelating agent. That type of agent which forms chelate is called complexing agent or chelating agent. EDTA is a good example of chelating agent. In EDTA, a pair of unshared electron capable of complexing with a metal ion is located on each of the 2 nitrogen atoms. So you see that when a pair of, there is no fundamental difference between a coordination compound and a chelate compound. Except in a chelate, there is a ring influence the stability of the complex. So normal complex and chelate complex, there is no such differences. But one difference is that the chelate complexes are stable. Chelate complexes are stable. Thus, a chelate can be described as a heterocyclic ring structure in which A metal atom or ion is a member of the ring. The stability of the chelate is usually much greater than that of corresponding unidentate metal complex. The structure of some of the commonly used polydentate ligands are given below. So you can see here diethylene triamine pentaacetic or pentaacetate, you can say DTPA, then you can say DCTA, trans 1,2 diaminocyclohexane tetraacetic acid, like this. Then next one is estimation. Okay, so after knowing this coordination compound, now we go to the estimation part. Okay, what do you mean by estimation of redox and complexation equilibrium studies? The solubility of a metal chelate in water can be attributed to the presence of hydrophilic groups such as COOH, SO3H, NH2, and OH. Remember, if any complex is soluble in water, it depends on the stability of metal chelates. Means it is a ring complexes, ring compound containing coordination compound. It is it is chelate, it is soluble in water if it contains which type of chelate compound? COOH containing chelate group, or SO3H, or NH2, or OH. If the chelating agent contains acidic as well as basic group, if the chelating agent contains acidic or basic group, the complex formed is soluble over a wide range of pH. The complex formed is soluble over a wide range of pH. So it is a conclusive statement that if a chelate complex contains COOH, SO3H, NH2, and OH group, then the complex is soluble in water, or you can say that if the chelate agent contains acidic as well as basic group, both acidic and basic, then the complex formed is soluble over a wide range of pH. In absence of these groups, the solubility of the chelating agent and the metal chelate are low. So that complex or chelate is soluble when it contains acidic and basic group. If the chelate does not contain these groups, then the chelate is not soluble in water. However, such chelates may be soluble in organic solvents. The chelating agents that form water-soluble complexes with or polyvalent metal are called as sequestering agents. Sequestering agents. See, the chelating agent that forms water-soluble complex with or polyvalent metal, then it is called a sequestering agent. This squeeze, this squeeze out, this squeeze out the metal from the solutions is called sequestering agents, you can say also. Okay. Next is a sequestering agent may be defined as a substance that apparently removes a metal ion from a solution by forming a complex ion that does not have the chemical reaction of the metal ion that is removed. Okay. For example, ethylene diamine tetraacetic acid, or EDTA, is a type of sequestering agent. Sequestering agent. It reacts with the most polyvalent metal ion to form water-soluble complexes, which cannot be extracted from aqueous solution with organic solvents. On the other hand, the okay. On the other hand, the dimethyl glyoxyme is also a forming a complex. Salicylaldoxyme also form complexes, but they are insoluble in water. So I have told you two things: complexes soluble in water and complexes not soluble in water. The complexes which is soluble in water is this one. Which one? Is the EDTA complex. And the complex which is not soluble in water is the dimethyl glyoxime and salicylodiene complex. So both the structures are given here below. You can see it. The for structure of dimethyl glyoxime, and also you can see salicylal doxime. The one is salicylal doxime, other one is dimethyl glyoxime. They form insoluble complexes in water. EDTA forms chelate with particularly most of the metal ions, and this is the fact it is exploited in the complexometric determination of these ions using EDTA. Such titrations are called complexometric titration or chelometric titration or EDTA titration. So EDTA titration is very important, and here EDTA is the selecting agent. Okay. Then on the favorable condition also, more than one metal ion may be present in the complex. In case of two metal ions are present, the complex is called binuclear complex. If two metal ions are there, it is called binuclear complex. And if there are more than two metal ions, that complex is referred to as a polynuclear complex. So if two metal ions are there in the Fe2CO9, you know it, Fe2CO9, it is a metal carbonyl, but there are two iron and 9 carbon monoxide ligands are there, and they are attached in bridging form, in terminal form. These things we have already studied in your BSc classes. So here I am explaining you that you have mono metal complexes, dimetal complexes, or polymetal complexes. Okay. The formation of binuclear and polynuclear complexes is favored by the formation of complex using high concentration of the metal ion. For example, zinc 2 plus and Cl minus ions react to form binuclear complex Zn2Cl6 2 minus, Zn2Cl6 2 minus. Here Zn2Cl6 2 minus means there are two zinc atoms and 6 number of chlorine atoms, Zn2Cl6 2 minus. Next is metal ligand equilibrium. Metal ligand equilibrium. Okay, we will now discuss it. For example, consider a metal ion. It is cadmium 2 plus, as written in your book 11.2.2, and you have a ligand ammonia. So cadmium 2 plus and ammonia, when they react, you get the complex CD NH3 whole 4 2 plus. CD NH3 whole 4 2 plus. CD NH3 whole 4 2 plus. So tetraamine cadmium 2 complex. So if it is an equilibrium reaction, as it is an equilibrium reaction, you can write equilibrium constant or formation constant. Actually, it is called formation constant because a new compound is formed. Okay, you can say also equilibrium constant, same thing. So anyway, when you write the formation constant Kf, then definitely the formula is concentration of product by concentration of reactant. So you have CD NH3 whole 4 2 plus by CD 2 plus concentration into ammonia to the power 4. CD NH3 whole 4 2 plus. CD NH3 whole 4 2 plus by CD 2 plus and NH3 to the power 4. NH3 to the power 4. 1 minute. Okay. So Kf is equal to, so and the value comes to be 5.5 10 to the power 7, a value. No, not need to remember. So Kf is there. And remember, if you divide Kf by 1 by Kf, means reciprocal of Kf, it gives you dissociation constant. Very interesting. The reverse of the reaction is characterized by another constant called dissociation constant. So this, because you know it, because the complex is formed, it undergo dissociation to form metal and ligand. So dissociation constant. So dissociation constant is the inverse of the what? Inverse of your um, formation constant. So CD2 plus into ammonia to the power 4 by CD ammonia 4 whole 4 2 plus. Generally, the complexation reaction occur in a series of steps. The reaction between CD2 plus and ammonia given above also occurs in the same way and involves four successive steps. And how it occurs, you can see. First of CD2 plus combines with 1 mole of ammonia, forming CD ammonia 2 plus. Then CD ammonia 2 plus ammonia, it gives you CdNH3 whole 2 plus. Similarly, CdNH3 whole 2 plus aqueous in aqueous medium plus ammonia gives CdNH3 whole 2 plus. Then CdNH3 whole 2 plus ammonia gives rise to CdNH3 whole 4 2 plus. CdNH3 whole 4 2 plus. So as all the steps involves equilibrium reactions, it becomes somewhat difficult to ascertain which of the series of reactions is described by the formation constant defined above. In order to resolve this issue, stepwise formation constants have been written. Means each step, you can see here, 4 steps are there because first step ammonia added, again ammonia added. So K, you can say the K1, K2, K3, K4, they are called stepwise formation constant, or you can also call stepwise equilibrium constant, K1, K2, K3, K4. On the other hand, when you write overall or cumulative formation constant, it is called beta. So beta is equal to K1 into K2 into K3 into K4 into K5. Means if you multiply all the dissociation stepwise dissociation constants in a particular reaction, then it becomes equal to beta. And beta is equal to cumulative formation constants. Cumulative formation constants. Okay. Similarly, take an example of one more example. Let's take an example of precipitate of AgCl. The solubility of AgCl increases in presence of excess fluoride due to the formation of complex AgCl2 minus. So one more thing. And the solubility of AgCl, you know AgCl is not so much soluble, it is sparingly soluble, AgCl. So when AgCl is treated with Cl minus, it gives you AgCl2 minus. AgCl2 minus. This AgCl2 minus is a complex. So when a complex is formed, its solubility increases. So remember, AgCl2 minus is soluble. Therefore, AgCl is, I can say, Ag forms a complex. Therefore, AgCl is more soluble in potassium chloride or any solution where Cl minus is there. The reaction can be written in this way. First of all, AgCl dissociates to give you Ag plus and Cl minus. This is simply your KSP. We have read this thing, solubility product. KSP is equal to Ag plus concentration into Cl minus concentration. KSP. Then you see Ag plus Cl minus Ag plus gives rise to AgCl. In the reverse reaction, then it will be K1. Then AgCl by Ag plus into Cl minus is your dissociation constant K1. Then AgCl. So first of all, AgCl break down to give you Ag plus Cl minus. This is your Ag plus Cl minus. This is your solubility product or KSP. Then Ag plus and Cl minus become AgCl. It gives you K1, and AgCl plus Cl minus again gives you AgCl2 minus. It is K2. So the equilibrium constant for the above reaction would therefore be equal to KSP into K1 equal K1 into K2. So KSP, if you cancel this, you get Ag plus 2Cl minus AgCl2. So KSP is equal to K1 into K2. Factors affecting solubility. Factors affecting solubility of metal ligand complex. So some of the metal ligand complex are quite stable. However, we cannot say the same for all the complexes. The solubility of complexes, please 1 minute, students, please 1 minute. Okay, we'll continue again. So now look at this one. Remember that when we are discussing about various factors that affect the metal ligand complex formation, one of them is nature of the metal ion. Second one is nature of ligand. Third one is basicity of ligand. Very interesting thing we discuss today. Size of Chillet ring, nature of metal Chillet ring, resonance effect, steric effect. These are some of the factors which is influencing the metal ligand complex. One is nature of the metal ion. The nature of the metal ion determines the type of bonding with the ligand donor atoms. More the electrostatic character of the bond, stable the complex. Therefore, small ion with a high charge lead to stronger complex. Small ion with high charge. Remember, question definitely come from this one 11.2.3. Then how can you judge the stability of a metal complex and the various factors affecting it? Then this is the factors I'm discussing. Smaller the ion with a higher charge, then lead to stronger complex. Then nature of ligand. The nature of bond formed between the ligand and the metal ion also influence the stability. Sorry. The nature of bond formed between the ligand and the metal ion also influences the stability. More so, the ligands forming chelate impart extra stability. The ligand forming chelates impart extra stability. For example, the complex of nickel with hexadentate ligand eh, has extra stability. Nickel with hexadentate ligand because the ligand is of 10 to the power 10 times stronger than simple ammonia. So remember the hexadentate ligand EDTA, for example, is 10 to the power 10 times. See how much big the value is. 10 to the power 10 times more stronger than the ammonia ligand. Therefore, stability also varies according to that. Basicity of the ligand. The stability of a series of complexes can be correlated to the ability of the ligand to accept a proton. Greater the basicity of the ligand, greater the stability of the complex. Any ligand which is more basic, for example, if I will say carbon, one ligand is carbon monoxide, one ligand is ammonia. Then which one is more basic? This also affects the stability of the complex. But remember, carbon monoxide or carbonyl ligand is the most in electron in the series of we can say the ligand series. It is at the last. Cyanide and carbon monoxide, they are at the last. Most stable complexes. Most stable complexes, you can say. They form most stable complexes. Okay. So again, we'll return to the uh, in between. Therefore, no issues about it. Hello, you are on online, students.
Yes, sir. Yes, sir.
Okay,
Yes,
okay, okay.
sir.
because actually I'm working in the office, so sometimes some important things comes in. Therefore, a problem arises. Okay, no issues. Okay. Now, actually, I'm working in the Department of Higher Education. Okay. Therefore, as I'm in office, so many people come and um, ask me different things. So we have to attend small calls. So no problem. Okay. So now we'll go to the size of the chillet ring. So if the chillet ring size is a maximum or bigger than a smaller size chillet, then it is more stable. More normally 5 and 6 member chillet rings are of maximum stability. The number of metal chillet rings, the stability of the complex is directly related to the number of chillet rings formed between the ligand and the metal ion. The stability of the complex is directly related to the number of chillet rings and formed between the metal and ligand ion. For example, there are two chillet rings are there or three chillet rings are there. Then number of chillet rings if more, then stability also more. The next one is resonance effect. The formation of a 5 or 6 member ring can be explained in the terms of conjugative effects. For example, a ring is there. Inside the ring, you have double bond, single bond, double bond, single bond. You know conjugation. Conjugation means a double, then a single, then double, then a single. If this type of conjugation is there, then it is called as the resonance stabilized. If it is more stable, it is more stable. So we have to take this one. It is a more stable one. Then steric effect. The steric effect refers to the size of the ligand, their spatial arrangement, and the distances between the coordination sites. These also play an important role in the stability of the complex. Okay, then we have to go to principles of complexometric titration. It is not so important, but remember titration means there must be a titrant and titrate. So two things are there. A complex of metric titration means it is the one in which the reaction between the analyte and the titrant involves the formation of a complex. The earliest titrimetric application involving metal ligand complexation were developed by Justus Liebig. This pertains to the determination of cyanide and chloride ions using Ag plus and Hg2 plus ions, respectively, as titrants. The complexes formed being AgCN2 and HgCl2. Okay, so it is a complex formation. Complexometry means complex formation. 1 minute. Okay. So EDTA an important chelating agent. EDTA is available in pure form but cannot be easily used as a primary standard. The solution of EDTA are prepared from its soluble disodium salt Na2H2Y.2H2O. The disodium salt is generally preferred as it is non-hygroscopic, water soluble, and a very stable sequestering agent. However, it will must be dried at 80 degrees Celsius for several days to obtain the precise composition of the dihydrate. In any case, sterilization of EDTA against a solution of metal ion to be determined helps to eliminate any error in endpoint determination. So, though EDTA has been extensively exploited for quantitative determination of the metal ion, it cannot be used for direct analysis of the ions or neutral ligands. Okay. Next one is you can see the EDT titration and pH. During when you titrate again with EDTA and you determine the pH of the solution, then you can see that pH value, pKa value of EDTA is pK may be pKa1 maybe 0, then 1.5, then 2, then 2.66, then 6.16. So different pKa value, the concentration of the solution has been measured. This is not this is a practical method, so we should not discuss this in detail. The practical method. So nothing can be done now in this stage. Okay. Now one example. See, the question is asked: compute the concentration of free Ca2 plus ion in a 0.1 molar solution by CaY2 minus at a pH equal 6.0 and at pH equal 10.0. Use the data given in 11.11 and 11.22. Ca2 plus EDTA, reversible sign CaY2 minus. Ca2 plus EDTA is equal to CaY2 minus. So Ca2 plus is the metal ion, EDTA is the chelate ligand forming a complex. At applying Ostwald's dilution law, you can calculate the pH, K means the equilibrium constant, from where you can calculate pH. Okay, now we'll discuss about effect of other complexing agents. You know, only EDTA is not a complexing agent. Many other complexing agents are there. For example, ammonium chloride, ammonia buffer, ammonium chloride, ammonia buffer. The ligand ammonia is present, for which may form several stable Mn plus ammonia complexes. For example, in the titration of zinc with EDTA in presence of ammonia buffer, the metal ion forms 4 different ammonia complexes as given below. ZnNH3 whole 2 plus by zinc 2 plus ammonia. So ammonia and ammonium chloride buffer is presently used for various stable metal ammonia complexes formation. So we can say buffer solution is also used to prepare the metal complexes. Some common metallochromic indicators and their useful pH. Metallochromic indicators are when during this titration also you are adding some indicator. They are calmagite, then areochrome black R, areochrome blue R, murexide, pan out salicylic acid. So calmagite, areochrome black R, areochrome blue R, murexide, pan out salicylic acid. Useful pH range is 9 to 11, 7.5 to 10.5, 8 to 12, 6 to 13, 2 to 11, out 2 to 3. So one is the some common metallochromic indicators are calmagite, eriochrome black R, eriochrome blue R, murexide, pan, and salicylic acid. The number of metallochromic indicators are available. However, for any such indicator to be used for the visual detection of endpoint in complex symmetric titration must meet the following requirements. So, thing is that you may use any indicator, but it must have a set of conditions. The conditions are because an indicator means what? To indicate the endpoint where the neutralization takes place. But that endpoint is to be visualized basing on the indicator used. An indicator must satisfy these conditions. One is the color reaction must occur at the end point, because at the end point if there is no color, then you cannot say that it is formed. So the color reaction must occur at the end point when nearly all the metal ion is complexed with EDTA. So when all the metal ions are being complexed by using EDTA as a ligand, then the color reaction must occur. Second one is that the indicator must be very sensitive to metal ion. Means for a particular metal ion, the indicator must be very sensitive so that the color uh, change occurs as near to equivalence point as possible. Therefore, it is very much sensitive to a particular metal ion. Third one is the color reaction should be specific or selective. The color reaction should be specific or selective. The color reaction should be specific or selective. Next is the color contrast between the free and the metal bound indicator complex. Please, students, please wait for a minute. So now, okay, the next one is this. Next point is the color contrast. The color contrast between the free and the metal bound indicator complex should be really observable. Means their color should be observable, otherwise you cannot see the end point. Next one, the metal indicator complex must possess sufficient stability, else it would not display a sharp color change. The metal indicator complex must possess sufficient stability, else it would not uh, display a sharp color change. Further, the metal indicator complex must be less stable than the metal EDTA complex. The metal indicator complex must be less stable than the metal EDTA complex. This is to ensure that at the end point, EDTA is able to remove all the metal ions from the metal indicator complex. It is desirable that the change in equilibrium from the metal indicator complex to the metal EDTA complex should be sharp and rapid. Okay. Then we go to one more iteration That is called potentiometric method. In potentiometric method, normally we are using the Nernst equation. Potentiometric determination of endpoint in complexometric titration can be used only for those ions for which specific ion electrodes are available. This is so because since there is no change in oxidation state during the titration, therefore a redox couple and a suitable indicator electrode or an ion selective electrode is a prerequisite for the purpose. It is however possible in case of some metal ions to perform the titration with a complexing titrant using indicator electrode constructed from the same metal. The potential at the indicator electrode in such a situation would be determined by the half cell, and the half cell is reduction half cell Mn plus N is equal to M, and according to Nernst equation, E is equal to E0 Mn plus by M minus 0.0591 by N. N is the number of moles of electron, log 1 by Mn plus the concentration. So a saturated calomel electrode is generally used to complete the cell. So remember, always in potentiometric titration, it is in plus 3 also. In potentiometric, it is a practical experiment, potentiometric method. So remember, students, here that in this case, a saturated calomel electrode is generally used. A saturated calomel electrode is generally used to complete the cell, as the potential at the indicator electrode depends on the concentration of the free ion, whose concentration decreases during the titration. The cell potential also changes. In the vicinity of equivalence point, there is an abrupt change in the pH value, which in electrode can be made sensitive to EDTA ion and can be used for endpoint determination as explained. Next one is, so anyway, so calomel electrode is used as a reference electrode to complete the cell in potentiometric titration, and the half cell is Mn plus Ne is equal to M, and it follows the Nernst equation. Then amperometric method. Amperometry is an electroanalytical method of analysis in which the information about the analyte can be obtained by measuring the current developed on a microelectrode as a function of applied potential. The mercury electrode used for following titration consists of a drop of mercury in contact with the solution containing the metal ion. So here mercury is used. EDTA is the titrant here. The half cell potential is determined by the formula Hg/Hg Y2 couple. Okay. Then we go to application of complex titrations. So many applications are there regarding the complex titration. One is called back titration. One is called direct titration. One is called replacement titration. And then it is called as the selectivity in complex metric titrations. Students, can I take a break of 2 to 3 minutes before I start this
Okay, sir.
Yes, sir, sure.
Okay, sir.
application of complex titration? I should take a break of 2 minutes. I should take water and something. I will start. Okay.
Okay, sir.
Okay, sir.
Okay, we will again continue. So there are many applications of complex titration. One is direct titration, then back titration, replacement titration. These three are most important thing, and last one is the indirect titration. Then selectivity in complex titrations. See, the selectivity means EDTA is a very unselective reagent because it complexes with a wide variety of metal complexes. So everywhere you cannot take EDTA to form complexes and use in titration because EDTA is a unselective reagent. It can form complexes with many metal ions. In such a situation, it becomes difficult to determine a given metal ion in presence of another ion. In this case, in order to achieve some kind of selectivity, we need to exploit the difference in the stability of the metal EDTA complex. There is a number of strategies have been evolved to perform selective determination of ions. This in turn increases the applicability of the complex iterations, and some of the common strategy are use of making and use of masking and demasking agents, pH control, classical separation, solvent extraction, kinetic masking. Masking and demasking means what? First of all, masking may be defined as a process in which a substance without physical separation of it or its reaction products is so transferred that it does not participate in a reaction. In simple word, its reaction is masked. In the act of demasking, the ability of the masked substance to participate in the reaction is recovered. In masking by complex formations, these masking agents are employed that form more stable complex with the interfering metal ion that meshed with the ions of analysis. See, masking means what? Mask means what? Mask means a cover. So if so many metal ions are there in a solution and you want to titrate against EDTA, then what you do? The ions, those are not required for titration, you have to mask it. For masking, you will use separate reagents, separate ligands. That ligands will form complexes with the metals which we do not want. Hence, we can able to do the titration of the metal ion which is our requirement. So the non-required metal ion should be masked or should be blocked by using new reagents. This is called masking and demasking. pH control, this is a method based on the difference in stability of the complexes formed between the metal ion and the chelate ligands. As we have learned earlier, that the formation of metal chelate is dependent on the pH of the reaction medium. The formation of a metal chelate depends on the pH of a medium. For example, in a weakly uh, in a weak in a weakly dissociated solution, chelate of bismuth, iron 2 plus or chromium 3 plus are readily formed at this end. Thus, in acidic solution, bismuth can be effectively titrated with chelating agent in presence of alkaline earth metals. A mixture of bismuth and lead ions can be successfully titrated by the fast titrating agent bismuth at pH 2, and okay, this is not so much important. Then classical separation, solvent extraction, and kinetic masking. Okay. Next is your some question answers regarding this chapter. Enlist the key steps in designing a typical complexometry determination. EDTA is a versatile complexing agent. What are its limitations? EDTA is a versatile complexing agent, but what are its limitations? It is unselective. It can form complexes with many metal ions. So this is you cannot use EDTA always during titration to form the complexes, because it can form if a solution contains many ions, many metal ions, then it is unselective. It can react to all. So how can you determine the concentration of one particular ion? Therefore, you have to. It is not used for that purpose. It is one of the drawback of it. Then, what are the essential requirements for a metallochromic indicator to be used for complex summit titration? What are the essential requirements for a metallochromic indicator to be used for complex symmetric titrations? CD2 plus, for example. One more thing. What the principle of spectrophotometric determinations? Like this. So many questions are there and the answers are there also. Also, sometimes it will come on a stepwise dissociation constant. Then how to calculate the formation constant from dissociation constant. So like simple, KD is equal to 1 by KF, or KD and KF, KD into KF is equal to 1. So similar things are there. Similarly, metallochromic indicators means what? I've told you, metallochromic indicator means, or metal ions indicators are the compounds that are capable of forming a complex with a metal ion being determined and can be used to determine the end point in the complex symmetric determination of the metal ion. The metal indicator complex has a lower stability constant than the titrate metal complex, and has an intense color which is distinctly different from the uncomplex indicator. In the beginning of the titration of the indicator forms a uncomplexed metal ion, and solution bears the metal ion indicator complex. Then a simple question will come, how to choose a suitable complexing agent, how to choose a suitable method of detecting the endpoint. These type of questions also comes. Okay. Then we'll go to the next chapter. Some doubts we'll discuss. Then we'll move to the next block. Prakash. Block number 4. Unit 10, some important things are there. We'll discuss this one. Then we'll go to the next thing. Unit 10, there's one thing I have left out that I'm discussing here, is the electrochemical cell estimations Redox indicators are discussed. I have discussed it in thoroughly. Yes, then redox titration in non-aqueous solvents discussed also. I think many things have been discussed. I will discuss some questions based on this unit 10. Unit 10. One is the, for example, you have a reaction given MnO4 minus plus 8H plus MnO4 minus 8H plus 5E, then Mn2 plus 4H2O. Here E cell equal to E0 cell minus 0.059 by 5. Why 5? Because 5 mole of electrons are there. Log right side. Right side is what? Mn2 plus water. Water doesn't change its volume or concentration does not change at all due to its large amount. So H2O concentration is remains as 1. So it is not written. So E0 E cell equal to E0 cell minus 0.059 by 5 log Mn2 plus concentration by MnO4 minus concentration into H plus concentration to the power 8. Why to the power 8? Because the number of moles written on the left side, 8H plus, means you write H plus to the power 8, means concentration to the power 8. So question will come, a reaction will be given to you. You have to write its Nernst equation. Remember, a reaction will be given to you, and you write the Nernst equation, and the Nernst equation is E cell equal to E0 cell minus 0.05 n by n log 1 by concentration of the things. So E cell equal to E0 cell minus 0.059 by 5 log 1 by Mn plus 2 by MnO4 minus into H plus to the power 8. So then also you can calculate pH. For example, pH is 1, then calculate the concentration of H plus ion. You can calculate it. And one more is it possible to, is it advisable to use a non-aqueous medium of titration for determination of compounds with an insoluble water? So questions, answers are there. It is the decreasing order of the oxidizing capability of the oxidizing agent is MnO4 minus, IO3 minus, Fe3 plus, H plus, and zinc 2 plus. The decreasing order of the reducing capacity of the reducing agent is in the order I minus, then this is a very good reducing capacity, whereas the MnO4 minus is very good oxidizing agent. Okay, what is remaining in the unit 10? I am discussing next class. We will start the redox, the block number 11. But here I will see. Okay, one more thing I have left also. This thing, so we'll discuss it now. That is called as the electrochemical cells discussed in the last class. Okay, I will slightly have more discussion here. In electrochemical cell, there are two half cells are there. Oxidation half cell on the left side, reduction half cell on the right side. And both the half cells are joined by a salt bridge. Both the half cells are joined by a salt bridge. A salt bridge is there, which is connecting both the solutions, saturated K plus and Cl minus solution. The salt bridge contains K plus and Cl minus solutions. It is saturated. And salt bridge, when we are using this salt bridge, it is simply that both the solutions, both the beaker are connecting to each other through a salt bridge. So salt bridge connecting the or completing the cell circuit, and it maintains the neutrality of the electrochemical cell. Zinc sulfate is the solution in the beaker 1 where zinc is dipped in it. So here zinc loses electron and becomes zinc 2 plus ion. So electrode is now becomes electrode loses electron, and similarly ion, and similarly zinc 2 plus ion is produced, and in the right side the copper 2 plus ion gains electron, loses by zinc, and it becomes copper. So copper deposited on the surface of the electrode, and you can see the color also means copper deposited, and here you can see left side it is colorless because zinc ions are produced. The salt bridge contains nitric potassium nitrate and agar gel, KNO3 and agar gel. The salt bridge contains inert electrolyte KNO3 in agar gel. The salt bridge contains a saturated solution of inert electrolyte like KNO3 in agar gel. In such a situation, the electrons are transferred by means of external circuit and within the cell. The current is carried by this. The electron transfer continues until copper 2 plus and zinc 2 plus concentration achieves a level corresponding to the equilibrium for the reaction. So zinc plus copper 2 plus gives rise to zinc 2 plus copper. When this stage is reached, there will be no further flow of electron. It is important to note that the overall reaction and the position of its equilibrium is the same regardless of the number in which the reaction is carried out. An electrochemical cell is capable of producing electrical energy because of tendency of reacting species to transfer electron and thus achieve the condition of equilibrium. A cell operated in such a way is called the galvanic cell. So electrochemical cells are also called galvanic cells. So electrochemical cells are those cells in which redox reaction takes place, and you can see that electrical energy is produced because of the chemical reactions. A cell operating is called galvanic cell. The voltage produced by an electrochemical cell is directly proportional to the equilibrium constant. Also, So, so students, can I take a few minutes break and I will start again. Last portion. Okay.
Okay, sir.
Okay, sir.
Okay. Okay. So, okay, students. So therefore, again we'll continue it. Thing is that always remember that electrochemical cells are not always accompanied by gain or loss of electrons, but it has many things to say. Always remember it. The things is that Nost equation is mainly applicable for doing this one. Nost equation is very important. Question will come, problem will come on from Nost equation. Nost equation is based on the electrochemical cell, which is in which the concentration is not unity and concentration varies. For example, concentration is 0.01 or 0.02 and temperature is not 298 Kelvin, something else. So concentration, pressure, temperature is varies. Then the electrochemical cell is not able to calculate the potential. In that particular case, we are using the Nost equation. The Nost equation is coming which used to calculate the E cell, but not E0 cell. E0 cell is the standard EMF. For example, you know the standard EMF means the reactions in which the concentration is unity and pressure is 1 bar. When pressure is 1 bar, then it is called a standard condition. At standard condition, the EMF of the cell is E0 cell, but at normal condition, at any concentration, at any pressure, you have to calculate E cell, and E cell is equal to E0 cell minus RT by NF ln 1 by Mn plus the concentrations. And also, you know, Faraday's F is the Faraday's constant or Faraday. F is equal to how much value? 96500 Coulomb. That's all we discussed it. So many parts have been discussed, nothing much left in this topic. So I think everything I have discussed. Anything more you want to ask me, you can ask. Otherwise, in the next class, we will at block 11. Nothing left in this topic. All the 10th block 10 is already completed. Anything you want to ask, you can ask. Many electrochemical cell redox reaction, complex metal titration, then complex means ligands, then metal ions, stability complex, chelates complexes, how to calculate equilibrium constant, how to calculate dissociation constant, how dissociation constant relates to formation constant. These questions will come. Any doubt you can ask me. If you have any doubt, you can ask me, no problem. And tomorrow we don't have any class. The class will be on Monday as it is. Because it may not be possible to take class. If I can take, then okay, I will tell you. But how can I convey you? That's the main problem. Because they have to admit, na? I cannot admit, I think so. So the class will be on Monday, same time. No class tomorrow. Okay? Any doubt you can ask me. Because if I will take class, then it will not be considered as a class. They will admit all these things are there. So class will be as per schedule. Okay. Any doubt you can ask me. No problem. Yes, I will share my. Yes, yes. Block for which units? Unit 10 and unit 11. Unit 10 and unit 11. Unit 10 and 11. Unit 10 and 11. Only block 5 left. And block 5 will be taught you on Monday and Tuesday. Only block 5 left. So any doubt you can ask me.
Sir, am I audible?
Yes, yes,
Hello.
you are audible, Mohandra. Yes.
Okay. Sir, I have one doubt regarding pH. Suppose we are taking the concentrate of solution of HCl and also we
Uh,
are taking the dilute solution of HCl. In the both
hmm,
case, pH value will
hmm.
be same or it will be changed.
Now, which value you are asking?
I am asking,
Which value?
suppose we are taking concentrate of HCl as well as
No, no, no,
I am
no, no.
again.
That value. See. First of all, difference is that concentrated HCl means it contains more HCl, and in dilute HCl means it's less acid, more water. So concentrated HCl is more acidic, its pH will be less. And in case of the dilute HCl, its pH is less. So it is the pH value is more. So pH value is nothing but the concentration of H plus ion, negative logarithm of H plus ion concentration. So both the solutions have different impact on electrochemical cell because the concentration changes means its electromotive force also changes. Different value.
Okay, sir. Okay, sir. So pH
And remember,
also it
yes,
pH, sir, it will be changed in the both cases. It will be not same.
yes, pH, definitely pH will change. Because you know
Okay,
pH is
sir.
the negative logarithm of H plus concentration. If H plus concentration is, for example, in dilute HCl, H plus concentration is nearly about 10 to the power minus 6. Okay, for example.
Okay, sir.
Then in concentrated HCl, pH value 10 to the minus 4 or minus 3. So pH will be 3. pH will be 3 in case of concentrated HCl, and pH will be more than 6 in dilute HCl. So pH is different.
Okay, sir. Okay, sir. Thank you, sir.
Thank you. Any more doubt? You can ask me, no problem. अरे बोले શું કરે खोल दियो बरोबर ભૂલ્યા ભાઈ રસ્તા ફોન કર સાસરે ફોન કર ફોન ટેકો ફોન લગા મને କଥା ହେବି પછી ક્લાસ લગા દે any doubt you can ask me આવશે આવજો okay આજ તો ક્લાસ થીલા thank you
Sir,
Hello.
no yes
sir, what is a kinetic masking?
see simple thing what do you mean by maxing tell me maxing means what
One cover
no
process in which substance
yes
without a physical.
yes maxing means see in a complex solution there may be many ions okay tell me yes or no
Yes, sir.
for example, you take a blood. Blood has many ions. Yes, so tell me yes. Iron ion, sodium ion, potassium ion, magnesium ion, zinc ion. So blood is a complex of many ions. Yes or no? I want to identify which ions are present. Then what I will do? I will do a titration with EDTA. But EDTA cannot only form complex with a particular ion. It can form complex with all the ions. So what I will do, I will mask all the ions so that EDTA can only combine with a particular ion. Clear? So kinetic masking means the metal ion does not form a complex due to its kinetic inertness. Is called as kinetic masking. Means we will use such a reagent or such a ligand so that it can simply form a strong complex and the reaction becomes very slow and it is called inert complex. This is called as kinetic masking. Means during the chemical reaction that particular complex will not play any role during titration and EDTA cannot do this. Okay.
Sir, what will be the ligand here, which will do the
Ligand,
masking? What we can do? Yes.
yes.
What ligand we can use?
Ligands, no, no, you have to say ligands in masking or what?
Yeah, yeah, ligand in masking. Yes.
See, many ligands are used, but the ligands mainly used in what you can say in the preparation of complexes are dimethyl glyoxyme, salicyloxyme. Dimethyl
Okay.
glyoxyme or salicyloxymes are mainly used. Or one more is called 2,3-dimercaptopropanol triethanol amine. These are mainly used as masking. And one more very simple one is the potassium cyanide. It is an effective
Okay.
masking agent. Potassium cyanide. Because you
Mm,
know why? Because cyanide ion is very stable ion. It is a very strong ligand. It can form a strong complexes. So strong complex that it will not break. Hence, therefore, potassium cyanide capsules are used by the terrorists. They always keep this tablet in their pocket. For example, somebody will cut them or will catch them, then immediately they will take this medicine, potassium cyanide, because potassium cyanide immediately dissolves in body, giving Cn minus ion, and this Cn minus ion can form complexes with the metal, and these complexes are so strong that the transportation of oxygen stops, and that particular person will die. Hence, potassium cyanide is an effective masking agent.
great, sir. Great. Thank you so much.
Any more questions? Otherwise, I will end this class. I think it is helpful to all of you.
Yes, sir. Yes.
Thing is that the chapter is very long, very large. Units, so many units are there, so it's not very difficult to explain everything in a short span of time.
Sir, any example of a kinetic masking?
Yes, I have told the example that using potassium cyanide during chemical reaction.
Okay,
Potassium
sir.
cyanide ion will form complexes with metal ion and stable complexes, and hence, see, formation of a complex is called masking. Yes or no? For
Yes, sir.
example, listen. For example, four ions are there. I want to react with only one ion. So three ions I have to mask them. Mask means what? Not to become unreactive. So how to mask them? Simply reacting with a particular ligand which can form stable complexes. So here the complex is the cyanide ion, but the compound used is potassium cyanide. Okay.
Sir, one more thing.
Okay. Last
This,
one. Last question.
yeah, last complexometric titration involve the reaction between analyte and titrant, right? It leads
What?
to formation of a stoichiometric complex, right?
Yes.
So, yeah. So, what this stoichiometric complex? What is the difference? What will be the difference between this complexometric and stoichiometric?
See,
Means it will
complex.
stay undissociated or what?
No, no, first of all, see, stoichiometric means what? Stoichiometry means what?
The
Stoichiometry
stoichio.
means, see, stoichiometry means, first of all, you should, complexometry means during a particular reaction, we are adding a particular reagent called a ligand to make a complex. This is called
Correct.
what? This is complexometry. Stoichiometry means, for example, when the metal ligand complex is formed, for take an example, EDTA. EDTA forms a cage-like structure. Yes, why cage? Because EDTA has six ligand sites, six donor sites. So it can form a cage-like. What is cage? When so many bonds are attached to a metal, it forms a cage. We can call as the stellate ligand. So EDTA forms a stellate ligand which is very stable. So the actual number of coordination sites depends on the size of the metal ion. However, all the metal ions with EDTA complex have 1:1 stoichiometry. See, stoichiometry means one, remember. EDTA is one, yes or no? EDTA is only one molecule,
Correct.
yes or no?
Correct. Correct.
So
Correct.
EDTA is one. For example, it forms a complex with copper 2 plus ion. So copper 2 plus is also one, yes or no?
Correct.
So the complex is EDTA. But really, you see, EDTA has 6 bonds of with copper, yes or no? So
Okay.
it
It
will be
forms.
6 is to 1. It will be 6 is to
Acha.
1. But actually, it is what?
Okay.
1 is to 1. Because we are going by the molecule, not going by its density. Clear?
Mhm.
So in complexometry, you see 6 bonds are formed, but in stoichiometry, it is only 1. Clear?
Okay. You mean to say EDT will, but say EDTA will form a 6:1 ratio, no, sir? So because it's a
No,
hexadentate
no,
ligand.
no, no. Now, in
Mhm.
stoichiometry, it is 1 is to 1. You take 1 mole of EDTA and 1 mole of copper ion. Clear?
Acha. Okay.
But in
Mhm.
complexometric cases, it forms 6 bonds are there. 6 bonds are there. So during
Okay.
titration, its concentration will change. And that change in concentration, we are plotting versus, we are plotting against the pH value.
Mhm.
So remember, in
Okay.
complex titration, a metal ion reacts with a complexing agent to form a color complex. The end point of titration is reached when the color of the complex changes. From that, you can able to determine that how much amount of calcium, how much amount of magnesium, zinc, or nickel present in that particular solution. Yes,
Correct. Correct.
because there, for example, in a hard, hard water contains calcium, magnesium. So how you know how much of hard water is hard? You will add complexing agent to make a complex.
Correct, sir.
Okay.
Mhm. Okay.
Any more doubt? Otherwise, time is over. So I will end this class today. Yes, I think.
Right, sir.
So today class, thank you very much for joining this class. So tomorrow,
So
but again,
Monday is our last
yes,
class now.
no, I think Tuesday, 5 classes happen.
Tuesday.
Now, how
Okay.
many
Okay. So
classes I've already?
only block 5 is there, no? I think.
I mean, block by, but it has 2 to 3 units, so it will take 2 classes. No?
Acha. Okay, sir.
Because the last class and today class is for block 10.
Hmm. Okay, sir.
Monday and Tuesday, I think you have 2 classes. You can see the schedule also, no problem.
Right, sir. Thank you.
Thank you very much. Thank you very much. Thank you all.
Thank you, sir.
Thank you. In calling, in, find the day.